Welcome. My name is John Perdiculius, and I'm with CompuPlast. We're a provider of simulation software and services in North America. And today I'd like to present a presentation on the applications of simulation in thermoforming. So as an introduction to the presentation, we're going to talk about thermoforming simulation, and in particular here I'm going to talk about the TSIM software, which is developed by Accuform in the Czech Republic. And we're going to talk about various thermoforming methods, positive, negative, with or without a cyst. We're going to talk about the benefits of the TSIM material model, because not all simulation software uses the same assumptions when they're modeling the materials. We're going to talk about the simulation steps, and then show various examples of the simulation being applied, and then finally finish up with a summary. So a little bit about the TSIM thermoforming simulation software. It was originally released in 1992, so there's well over 20 years of success with the software by many companies worldwide that have been using it. It's based on advanced modeling theory, non-isothermal, and a viscoelastic material model. TSIM uses the KVKZ material model, and I'll explain why this is important later on. It's a very versatile simulation. We can do either vacuum forming, pressure forming, with plug assists, and the software can handle up to 20 independently moving tools, so even a very complex thermoforming process can be modeled. And it's very, very efficient. There's a very fast project setup, fast and stable solvers, and a very efficient mesh refinement technique for setting up your project, running your initial simulations with lower mesh density, and then just boosting up the mesh density to get your final simulation result. Now it can be used to predict thickness distribution, webs and wrinkle formation in your forming, of course total sheet deformation or stretching, and this has implications in being able to predict image distortion, which is one of the features of the software. Of course, we can get the stress distribution in the sheet and the final stress, which can give us an indication of how stable our part's going to be. And it also has a cooling analysis, so we can predict the cooling time required for our part and get an idea of the cycle time we will need when we're making that part. So with these capabilities, the software can be used to optimize part mold design, and I have both the part design and the mold design here because you may want to modify the part to make it easier to form, or you may want to optimize the mold to avoid certain problems. Of course, plug assist design, there's a variety of different assists that could be created, and the software can be used to optimize that. We can do pattern or zone heating of the sheet, and I will demonstrate how we can use that to our benefit when we're doing a simulation. And of course, we can select the size and the thickness of the sheet that's the most optimum for our process and save some money with respect to the cost. So here's an example of what we call positive forming. The tool here is below the sheet, and in this video, the colors represent thickness. So you can see the sheet starts out at a uniform thick sheet, and then as the forming takes place, the tool comes up through the sheet. You can see the colors start to change. So here it is. I'm just going to pause it right here. At this point here, the sheet is being the tool is coming through the sheet, and the vacuum has just started to come on. You can just see the material starting to get pulled in, and you can see the thickness variations. And then as we proceed, there's some additional stretching, and we end up with our final thickness distribution. And the blue represents the thick areas, and the red represents the thin areas. Now all this can be quantified, of course, in the actual simulation. Just a note about how the graphics appear on the simulation here. Here we're going to have an example of positive forming with an assist. And by assist, we mean this bar right in here. This is the simulation of a refrigerator liner. And the bar, you can see, it kind of looks discontinuous. The sheet is given top priority on all the graphics, so it appears to be above the assist. But you'll see when I run the simulation here, the video, you'll see that this bar prevents the sheet from stretching and eliminates a web that it would occur down in here. So we have these two separate sections that we want to form, and we want to do it with one sheet. And so to avoid the web that would form in between those two sections, we use this bar to push the material down. And again, the blue is the thick areas and the red represents the thin areas of the part. Now here's the same video, but now we've replaced the color that represents the thickness with a grid that we've essentially painted on the sheet, and now we can get an idea of the amount of deformation that the material experiences. So here again, this assist is actually above this sheet, and you'll see here as it moves along, the assist prevents it from pre-inflating. And then at the end here now, based on that grid pattern being uniform at the beginning, you can see what regions of this sheet have stretched and how much they have stretched or deformed. And of course, once we can predict this, then the next step would be to put an actual image on the sheet. I'll talk a little bit more about image distortion later on in the presentation. The simulation can also do negative forming with undercuts. So in this simulation here, you can't see the sheet because it's just a line right here. But watch when I start the animation, you see the sheet pulls in and forms into the undercut area. Now, of course, this requires special mold design to allow part extraction, but the software is certainly capable of doing even this type of geometry. Now, you'll notice that the whole part isn't filled. We always take advantage of symmetry whenever we can in a simulation. So if you have a symmetrical part, if this part I believe is circular, we can only need to do, let's say, 1/4 of the part to do the simulation. So I'll show more of this later on. So here is negative forming with assist. Again, the assist is underneath. These sections here are cavities, and you'll see now when I start the animation what's happening. The assist pushes the material up into the cavities, and then the vacuum comes on and completes the forming. So I'll just run that one more time so you'll see it. The assist comes up, pushes the material into the cavities, and then the vacuum comes on and the material is pulled into those cavities to form. And again, the colors represent thickness, blue being the thickest area, red being the thinnest area. In addition to assist forming, and take it one step further, as I mentioned, the TSIM software has 20 independently moving tools. So when you're doing, if your machine has the capability, you can actually have the assists move to different position and different speeds and even different direction depending on how complex the part is. So if you have some articulated tooling or something that's a little bit more elaborate, based on the fact that each tool can move in its own direction, we can deal with very complex forming situations. So there's the assist, and then the vacuum comes on to finish the forming. And you can see this assist here has pushed the material down close to the bottom, so this is a relatively thick area here. Now, a little bit about material properties. The TSIM simulation software uses a KBKZ viscoelastic model, and it's very, very important to use this type of advanced model, even though it increases the simulation complexity dramatically and it makes it a little bit more unstable. It's really required over a simple hyperelastic model, because if you don't have a viscoelastic model, you cannot predict simple sagging of the sheet. which is shown here. So here we have this stepped cavity here, and the sheet is up here. So now I'll just play the video here. And this is the sheet sagging under its own weight. And if you had a hyperelastic model, the material could stretch down to a certain position, but it would not continue sagging with time, essentially right down to the bottom of the cavity. So this is why it's critical to have the correct model. Otherwise, you're not really predicting reality. Now, the steps that we use to do a thermoforming simulation are relatively straightforward. We need to import a tool or mold geometry. This includes plug assists or pressure boxes. Each forming item is considered a tool in TSIM, and that is imported typically as an STL file. There are some capabilities within the software to make simple geometries. Maybe you want to make a bar or add a flange to some surface that you've imported. But mainly you're going to create the tool files in some CAD program, export them in the STL format, because TSIM typically just needs the surface that's in contact with the polymer. So we import the tool geometry, then we define our sheet size, and typically what we need is the overall dimensions, the thickness, the initial starting thickness, our initial guess, the initial temperature of the sheet, the clamping region, what areas are going to be clamped, what areas are pressure areas. You can find no pressure areas that are going to be beyond the tool. It has a lot of capabilities there. Then we specify our process conditions, that is the tool movement, direction, speed, when the vacuum comes on or when the pressure comes on, and all the timing of all those things are specified within a spreadsheet type format, and that can be very, very well defined. Then we select the material from the database. TSIM comes with approximately 25 typical thermoforming materials, anywhere from ABS, polystyrene, HIPS, the acrylics, the basic materials that are commonly used. And then we also provide a means for customers to add their own materials, get the materials measured and add them to their database. Once we added that information, we run the simulation. Simulations are very fast, typically between, say, 5 minutes to maybe as much as 45 minutes to an hour, depending on the computer power. But most of them are typically around, once we bump up the number of elements we use for our final simulation, typically around 20 to 30 minutes. Then we analyze the results, called post-processing. We review the thickness distributions and so forth. And that's what I'm going to present a little bit about here. Once we look at the results, we either like what we see or we don't like what we see, and we go back up and we make a modification either to the tool, to the sheet thickness, to the process conditions, and then we repeat until we're satisfied that we have a good process that's giving us a uniform sheet thickness. So here's an example of how we might use the simulation to distinguish between two plug designs. So on the left, I have a kind of more standard hemispherical round bottom plug, and it's going to push this material. Now again, I'm using 1/4 symmetry, so I'm just modeling 1/4 of the sheet, and I'm trying to form this cup, maybe like a yogurt cup or something. So the assist pushes the material down, and then the vacuum takes place and stretches it. Now what I've done here is I've adjusted the scale to a maximum of, let's say, 20 thousandths, 30 thousandths of an inch, 0.7 millimeter, somewhere there. And so everything that's above that thickness stays blue, and that allows us to highlight the minimum thickness areas. And you can see with this assist, the minimum thickness has formed right in the kind of the corners, the round, the radius at the bottom of the cup. Now I'm going to run the same cup, but with another assist, This time my assist, you can see it's got a little bit of a concave bottom. And so here it pushes the material a little differently. It's a little larger diameter. And as you can see here, the thin areas are essentially this surface. So this wall has thinned down more. Down here we have a little higher thickness down at the bottom corner of the cup. And so based on the two different tool designs, we have two totally different thickness distributions in our product. And this is how we would go about optimizing our plug assist for the properties that we want in our final product. We can also do the temperature optimization. If you're making large parts, for example, this is a very large sheet that's, let's say, 2 meters by 1 meter. It was, in fact, it was a polycarbonate, used for a polycarbonate sign. And if we ran the simulation with an even temperature of 160 degrees Celsius for forming, even though it wasn't a very deep draw, we can see a relatively large thickness variation with thin corners here. And these corners were getting critically thin to the point where it would be easy to damage and crack the material here in these corners. And that's, of course, not desirable. So if we have the ability in our ovens to do pattern heating, then we can adjust the temperature distribution through the sheet. And here what we've done is we've asked the program to automatically optimize the temperature of the initial sheet between 150 and 160 degrees Celsius. So the blue area is the cold 150 degree, as you can see here, 152 degrees in this blue region, and the red area is 160 degrees. So this will tell us the optimum pattern heating that we need in order to get a more uniform thickness distribution throughout our final part. And so if we have the capability to put some heat shields in or program the energy or the heat zones in our sheet, then we can use this feature to determine the more optimum heating pattern. And as a result, we can go from something with a very large variation in thickness to a much more uniform thickness distribution and essentially a thicker overall average part thickness. The next example I want to show here is a motorboat housing. That's this region on this motorboat. And the tool for this, of course, because we're symmetric down the center, we only need to use half of it. The tool for this might look like this. So here's like a positive, like a male tool, and we would use this to do the forming. But as you can see, it's a very, very deep draw. And for these types of parts, what we'll do is we'll use a draw box or vacuum box. And basically, it's just a box where the material would sit up along here and get pre-drawn into this box to create more surface. And then once you insert the mold, you reverse the pressure and you pull the material onto the part. So this would look something like this. Again, due to symmetry, we only show half of the tools. So here's the process here in action. When we start, we pull a vacuum and draw the material into the box, insert our mold, and then turn the vacuum around and pull the material up against the mold. But as you can see here, and I'll just play that one more time, hang on. As you can see here, we're creating this large surface, and then when we turn around to pull that onto the mold, we create these webs in these corners. And so you can see here, these webs or wrinkles have formed into the part, and the TSIM software is very good at predicting these, their location, and so we want to avoid these web predictions, the occurrence of these webs. And so with the software now, we can try to find a solution that will prevent these webs from appearing and affecting our final part quality. So in this case, what they did was they put these corner pieces in the vacuum box or draw plate, which they were called web catchers, or just some additional surface that takes this material out of play. Now with the simulation, we can determine the exact position and size of these web catchers by using virtual trial and error. And we're not wasting any material, we're not wasting any time on the line, and we can optimize the exact position of these supports here. And once we do that, you'll see here that this material is essentially prevented from stretching out into the draw box. And then when the material gets pulled down, we don't have excess material to form the webs in the part. And as a result, the final part then is formed wrinkle or web free. Now here I've adjusted the maximum scale. If you see the previous slide, the maximum thickness is 9.54 and the minimum is 1.13. We want to see where the minimum area is, kind of how large it is. Our critical thickness is 3 millimeters on this final part. So when we go to the next slide here, I've adjusted the maximum thickness scale to read 3 millimeters. And so now anything that's below 3 millimeters gets highlighted, and we can see that this region right down in here is somewhere in the neighborhood, I would say maybe around 1.5 millimeters thick, below our critical value. However, our trim line is well above that region, and as a result, we're not concerned about this because all this gets cut off and then recycled away. So our part starts from here and up, and we can clearly see that everything is above the minimum critical thickness, so we'll have a successful forming. Now, as I mentioned earlier, TSIM also has the capability of studying image distortion. And here's an example here of a sheet that's printed with a bunch of just lines, in this case horizontal lines on the surface. And we have a plug assist forming 2 yogurt cups. And so you see the assist pushing the material down and stretching it out, and we can follow the deformation of the image. So where these lines started off as straight, you can see that they end up being curved on the final part. Now, if we can put this pattern on the initial sheet and then see what happens when the sheet is formed, how this pattern deforms, this is the traditional image distortion development method. They would put a grid on here, form it, and then use the deformation on the grid to determine how big the shape of a different image that they want on the final part should look like. And it's a trial and error procedure which can be done in TSIM. But we can take it a step further within the software. In fact, we can take the final part that's formed and then apply the image to that part as we want it. So we want these rings to be around the circumference at this spacing, and we want this top of this section here to have this blue color. What should the initial image printed on the sheet look like? And through a process of reverse engineering, what we can do is we can directly map this back to the initial sheet shape and say, if we're going to make a part that looks like this, this is what we need to print on the sheet prior to forming. So this can be very, very helpful when you're making a pre-printed sheet and want the image to appear a certain way. So for example, if I'm making a Halloween mask here, I want to know how I'm going to print the flat sheet so that when it gets formed, then the mask has the correct appearance that we want on the final product. And so you can apply the image on the final shape and then map that back to the flat sheet and then export that out for printing. There you can see that being formed. So in summary, thermoforming simulation offers accurate formed part thickness predictions. These are also very useful if you're going to do a stress analysis on your part, rather than assuming the final thickness that you want. And when you do stress analysis, sometimes you'll just apply the same thickness to all areas of the part. What you can do is you can take the predicted thickness distribution and map it to your stress analysis mesh, and then get a more accurate stress analysis by putting the more accurate thickness. We can predict webs and wrinkles prior to them happening and then find ways to avoid them. We have efficient mold part design and optimization because we're not wasting parts. As I mentioned about the that large polycarbonate sheet, each one of those sheets is $800 to $1,000. So each experiment you do can be very, very expensive. So within the virtual environment, we're not wasting any material or energy. And we have very efficient assist design optimization. You get a web or an unacceptable thickness distribution, and you might have 5 or 6 ideas on how to correct that. Rather than go and build all the different assists that are possible, you can sit in your office, run a bunch of simulations with the different options you have, and then select the 1 or 2 that have the best results to actually try on your production line. Same with pattern heating. We can get our initial guess of what sort of heat distribution we need, and what sort of shielding we might want to put on our part, and what sort of temperature variation, temperature range we might need in order to see a section that would normally be thin to have that part thicken up. And finally, because we can monitor the deformation of the surface, we can predict how the surface stretches. We can also then put an image on that surface and predict how that image will distort, or more interesting is to put the image on the final part shape and then map that back to the flat sheet and determine how the image should be pre-distorted so that it looks fine on the final part. With that, I'd like to thank you for attending the presentation, and I'd be pleased to answer any questions. If we don't get to your questions here, you can either send me an email or give me a call, and I can try and answer your questions through there.